Hello, welcome back everyone. I hope everyone's doing great. Mandar Chakrabarti here. Now in the last couple of videos, we have had an elemental introduction to the world of wireless technology and to the world of electromagnetic wave theory, and have discussed the various different applications where electromagnetic wave theory is implicitly required. And we have seen that the applications are superbly wide, ranging from the microwave oven that we use to cook our food, to the all-essential mobile phone that we use for our daily purposes, to FM channels that we listen to when we drive our cars, our television broadcast systems, all the way up to PET-CT scans and X-rays for advanced medical diagnosis. In this video, we would now want to start to understand the physics behind the electromagnetic wave theory. Understanding the physics of electromagnetic wave theory is crucial if we actually want to manipulate the electromagnetic wave theory for our own practical devices. As already discussed in the first lecture, vector analysis plays a crucial role in this understanding, and it's also elemental towards the upcoming lectures. And as such, it is necessary to have a brief recapitulation of vector analysis once again. In this video, I would like to recapitulate the concepts of vector addition and vector subtraction with all of you. So let's get started. Okay, so basically, if I were to consider what is a vector. Now, vector is a concept of mathematics. So, it is a mathematical representation of a quantity having both a magnitude as well as a direction. What's the difference between a vector and a scalar? The primary difference is direction. So, if I were to tell you, please walk 1 kilometer, then that would be a scalar situation. But if I were to tell you walk 1 kilometer north, then that becomes a vector representation. Let me elaborate a little bit more. If I give you two values, say x equals to 45 and y equals to 45, then you can very easily tell me that x is equals to y. But this is not so easy when it comes to vector representations. If I were to consider one vector, say something like this. Now, vectors are denoted with a cap on top of their head with an arrow like this. So, the magnitude of this is, say, 2 units. And I give you another vector, say a vector like this. Say I name this vector as b. And this one also is 2 units. Now, can you tell me whether these two vectors are the same? Yeah, these two vectors are not the same because the direction that the two of them are pointing are quite different from each other. Since the two vectors are pointing in different directions, therefore, I can say vector A is not equals to vector B. Now, you see, this gentleman over here, this man is a giant in the field of electromagnetic theory. Let me introduce you to Professor Walter Lewing. Professor Walter Lewing of MIT is one of the legends in the academic world in the field of physics, electromagnetism, and mechanics. So, I follow his classes on a regular basis, which are very easily available online. And I want to show you a very small excerpt from one of his lectures. I'll leave the link to the full lecture in the description of this video if you are interested. So, why don't we hear what Professor Lewing has to say?
There are quantities in physics which are determined uniquely by one number. Mass is one of them, temperature is one of them, speed is one of them. We call those scalars. There are others where you need more than one number. For instance, on a one-dimensional motion, velocity, it has a certain magnitude, that's the speed, but you also have to know whether it goes this way or that way. So there has to be a direction. Velocity is a vector and acceleration is a vector. And today we're going to learn how to work with these vectors. A vector has a length and a vector has a direction, and that's why we actually represent it by an arrow. You all have seen this is a vector. Remember this? This is a vector. If you look at the vector head on, you see a dot. If you look at the vector from behind, you see a cross. This is a vector, and that will be our representation of vectors.
Okay, so now that we have the basic gist, what Professor is trying to tell us is something like this, that since we are dealing with electromagnetic theory, then we are dealing with a three-dimensional world. So these sort of vectors that we have represented, these vectors are plain and simple two-dimensional vectors. So if I were to draw the coordinate axes, then it would be something like this. You have your x-axis and your y-axis over here. But in a three-dimensional consideration, let's say that I were to tell you that this is a vector. So if this vector is coming towards you, now this screen that you are seeing in front of you, this screen is a two-dimensional surface, right? So if this vector were to be coming out of the screen towards you, then by convention we represent that by a dot. And conversely, if the vector were to be entering into the screen, then we represent that by a cross like this. Alright, now what about a practical example of a vector? So let us consider an aeroplane is flying in the north direction. Now we are standing here on the ground and we are observing this aeroplane. So if everything were alright, then this plane would actually be traveling in the north direction. But we have a strong gust of wind blowing in from the west, and this would result, at least from our point of view, this is what we would observe to happen. Check it out. Right? So at least from our point of view, the plane will have drifted a little bit sideways. That is, it will go in a diagonal way. Now this can be explained practically with the help of vectors. You see, the green arrow marks the original intended direction of the airplane, and this yellow arrow marks the direction of the wind. So this marks actually the resultant of these two vectors, which is the direction that the plane finally took. And this what we get is from vector addition. So vector addition is slightly different from your general scalar addition. And I believe you should be familiar with this, but still we are going to have a very brief recapitulation of this. So vector addition can be done primarily in two different ways. The first method is the head to tail method, where we have, say I have two different vectors. Let me draw them for you. So I have one vector like this. I have one vector A in this direction, and I have another vector B in this direction. Now if I want to take the summation of these two vectors, then I want to join this with the head of this. So let me laterally shift this vector to this side, and what I get is this. So since I have laterally shifted, it remains the same vector, and the resultant of the resultant addition is in this direction. So this is A plus B. Right, it does not matter whether we take the tail of B and add it to the head of A, or we take the tail of A and add it to the head of B. It's going to give us the same result. Now, the next way that we can perform vector addition is known as the tail-to-tail method. Over here, we link the two vectors by their tail, of course. So, let's try that out. So, again, the two vectors, I have vector A over here and vector B over here. So this time we are linking the two of them up by their tails. So laterally shift this and bring it here, and this is what we get. And now we have to do a couple of more steps. Take another image of B, so what I get is this one, let's call that as B dashed, and take another image of A, what I get is this one, let's call that as A dashed. And what we'll end up with is a parallelogram that looks like this, and the resultant is given by this particular diagonal. This diagonal, this is the resultant, A plus B. So the two results that we got over here, A plus B, and the result that we got over here, A plus B, the two are going to be the exact same magnitude, pointing in the exact same direction. Now, vector subtraction. Well, vector subtraction, basically we approach it in a roundabout manner. So vector subtraction is your vector addition of the inverted vector. Let me explain what I'm talking about. So if I were to have any vector, say I take a vector like this, I have a vector, let's name that as vector B. Now, same magnitude, inverted direction, and that vector becomes the negative of the original vector, so it becomes minus of B. So A minus B vector is basically, A minus B vector is basically A plus of your minus B. So if you have any vector like this, vector B, then you invert it in the opposite direction and then you approach the head to tail method, and that gives you the result of A minus B. Alright, so that was a quick recapitulation of vector addition and vector subtraction. In the next video, we are going to be diving a little bit more deeper into the concepts of vector analysis. Because, as I said, vector analysis is extremely important when it comes to understanding the physics of electromagnetic wave theory. So, at the risk of sounding repetitive, if you enjoyed the content, then a sub to the channel would be really great. I bring out regular videos on the tutorial subject. Right now, we are going through a tutorial on the electromagnetic field theory. So, okay, alright, I'll catch you in the next one. Bye bye.